Hello, class. These are the video solutions for Lab 5.1. The first part of this lab, they ask you in your own words to explain how to find the following given a rational function. So for the domain, it's really all of the real numbers except the values of x that make the denominator 0. So if I were to scroll down and look at the second problem, when you see something like 2 over x minus 4, the domain would be all real numbers except x equals 4. Because if I were to substitute 4 in for x, I'd have 4 minus 4 is 0. So I'm not allowed to have division by 0. So the domain would be all real numbers except the value of x that makes the denominator 0. Okay. The vertical asymptote is the exception to the domain. So if I look at this problem again as an example, if the domain is all real numbers except 4, or except x equals 4, the vertical asymptote happens at x equals 4, right? So the exception to the domain is your vertical asymptote, okay? Your horizontal asymptote, there's two ways to find it. One way would be to graph the function in your calculator and then go to the table and see what happens to the values of x when x gets really large. So in your table, you want to make x really big and see what value you approach. Then make x really small and see what value you approach. And that value that you approach from the left and to the right is your horizontal asymptote, or the value of your horizontal asymptote. An easier way to think about it, I created this document, and I believe this is one of your previous videos. Think of it this way, right? You don't have to worry about this first case, right? For the purposes of our class, you'd really only worry about these two cases, where the degree of the numerator is less than the degree of the denominator, and then where the degree of the numerator is equal to the degree of the denominator. So what's the degree? The degree is the exponent, right? So you see I have x, it's really x to the 1, and on the bottom I have x to the 1. This second problem, I have x to the 2 and x to the 2. So the degree of my first problem would be 1, x to the 1 over x to the 1. So the degree on the top and the degree on the bottom are the same. The second problem, my degrees are still the same. The degree of my numerator would be 2. The degree of my denominator would be 2. Right? We always use the highest power. So for the first problem, since my degrees are the same, right? The degree of my numerator is 1. The degree of my denominator is 1. You can take the ratio of leading coefficients. So 12 over 3, right? Ratio means division. 12 over 3 is 4, so the horizontal asymptote would be y equals 4. The second problem, my degrees are the same, x to the second, right? So the degrees are 2. So you take the ratio of leading coefficients would be 10 divided by 5 is 2. Right? So horizontal asymptote would happen at y equals 2. But what about a case where the degree of the numerator is smaller than the degree of the denominator? Well, here, the degree of my denominator is 1, x to the 1. The degree of my numerator is 0. Since we don't have any variables on the top, my degree is 0. So since the degree of the numerator is smaller than the degree of the denominator, the answer is y equals 0. Okay, so anytime that the degree on the top is smaller than the degree on the bottom, your horizontal asymptote is y equals 0. Okay. Vertical intercept, well, that's simply sub in 0 for x and solve for y. And for the horizontal intercept, sub in 0 for y, solve for x. Okay. So on the second problem, we have some matching. On my test, I like to have you match graphs. So just look at the denominators. What value will give you an error in the denominator for each of these three problems? So for the first one, if x equals 0, I have a problem. So I would expect there to be an asymptote at x equals 0. So remember, the asymptote is where the break occurs in your graph, right? Where do I have to take my finger off the paper? Okay. So if you look, this is happening at 0, right? If I were to make a little imaginary dotted line at x equals 0, you see my graph, I have to take my finger off the paper at x equals 0. If you look at the next one, if I had x equals 4, I'd have a problem, right? Because 4 minus 4 is 0. So if I count 1, 2, 3, 4, notice we have a break here at x equals 4. So that's why I know this graph goes here, right? Graph 1 would go here, right? Letter C would match up with this graph. And then the last one, if I put negative 4 in for x, 2 times negative 4 is negative 8. Negative 8 plus 8 is 0. So x equals negative 4 would give me a problem. So I would expect that -1, -2, -3, -4 to have a break in my graph. So that's how we know that these two match. Okay. Question 3. All right, here's the rational function. Answer the following questions. All right, the domain will be all real numbers except what makes the denominator 0. So x equals 5 is 0. You can always just set x minus 5 equal to 0 and solve for x, and you still get 5. Right? If I take the denominator and set it to 0, when you solve for x, you end up with 5. So 5 minus 5 is 0. So all real numbers except 5. The equation for the vertical asymptote is the exception to this domain. So if the domain is all real numbers except x equals 5, the equation of the vertical asymptote is x equals 5. Right? It's your exception to the domain. All right. The next part, horizontal asymptote. Well, remember, going back to this document we had, if the degree of the numerator is equal to the degree of the denominator, take the ratio of leading coefficients, meaning divide. So in this problem, the degree of my numerator is 1, because it's x to the 1. The degree of my denominator is 1, because that's still x to the 1. So you take 2 divided by 1. Those are the leading coefficients. And you end up with y equals 2. All right, what they're showing you here is they're saying, okay, what if I graph this and actually make my table? When x gets really big, you'll see that we're at 2.02, 2.002, 2.0003, all the way down to 2. And if I make x really small, right, -1,000, -100,000, and so on, y becomes really small. So the number that you approach as x gets really big is 2. The number you approach as x gets really small is still 2. So your answer is y equals 2. I like this method better, right? Just simply dividing the leading coefficients. Right, simply dividing the 2 and the 1 to get 2. Vertical intercept, sub in 0 for x, solve for y. Right, as an ordered pair, 0, -3. Horizontal intercept, sub in 0 for y, solve for x. So here you notice we put 0 over 1, and then we simply cross multiply, right, to solve for x. And you get a -7.5, 0. Okay, and then on this lab, we had you do a quick review of factoring. So I have x squared plus 6x minus 55. So I can't solve this, but I can factor. And remember, you're going to ask yourself, what two numbers when multiplied give me -55, but when added give me 6? So 11 times -5 is -55. And when I add 11 plus -5, I get 6. So plus 11 and -5 are my two factors, right? X plus 11, x minus 5. Next one. Okay, well, first I can factor out a 7x, right? 7 is the biggest number that goes into each of these numbers evenly, and x is the value, x to the 1 is the variable with the smallest exponent, right? So you take the biggest number that goes into all three numbers evenly, and you take the x with the smallest exponent. So 3, 2, and 1, so we take x to the 1 out. Divide each term by 7x, and you're left with x squared, 5x, 42, right? If I divide 42x by 7x, I get 6. 35x squared divided by 7x is 5x. 7x cubed divided by 7x is x squared. And then you can factor this middle part, right? What two numbers when multiplied give me 6, but when added give me 5? Well, 2 times 3 is 6. 2 plus 3 is 5. Last piece, factor out a 5 first, right? Notice these all have 3 terms. This only has 2 terms. So I can't do that what two numbers when multiplied give me the last term, but when added give me the middle term. So I factor out a 5, and then divide each piece by 5, and you're left with x squared minus 1. And this is the difference of two perfect squares, right? X minus 1, x plus 1. That's it. Thank you for watching.